The universe, vast and indifferent, occasionally stages events that ripple across both the cosmos and our fragile planet, as if the machinery of stars and the tectonics of Earth conspire in a hidden rhythm. In late September, a rare alignment of celestial and terrestrial phenomena unfolded, capturing the attention of astronomers, geophysicists, and curious observers alike. Two novae ignited in the night sky, their intense light briefly piercing the darkness of the southern hemisphere, marking violent upheavals within distant binary star systems. Each explosion, though hundreds of light-years away, emitted bursts of gamma rays and X-rays, energy streams traveling unfathomable distances to reach Earth's telescopes and detectors. Simultaneously, the ground beneath Venezuela shifted violently, producing back-to-back magnitude 6.2 and 6. 3 earthquakes, their rupture waves radiating through the crust with a precision and force that seemed almost eerily synchronized with the cosmic fireworks above. Yet the terrestrial events were only half the story. In the void beyond, 3I Atlas, an enigmatic interstellar object, journeyed into the inner solar system. At the same time, a coronal mass ejection erupted from the Sun, a torrent of plasma and magnetic energy hurtling through space. The CME collided with 3I Atlas, bathing it in charged particles, ionizing its gases, and altering its coma in a visible dance of plasma, dust, and electromagnetic force. The confluence of novae, seismic events, and an energized interstellar object defied ordinary perception. Each event, remarkable on its own, occurred within a narrow temporal window, creating a cascading tableau of astronomical and geophysical phenomena. Observers noted the rapid succession of explosions in binary star systems, the tremors shaking Venezuela's crust, and the strange morphing tail of 3I Atlas, sometimes extending toward the Sun, at other times pushing away in anti-solar directions. Scientific instruments registered changes in radiation, plasma density, and electromagnetic fields, hinting at subtle interconnections across scales that challenged conventional models. It was as if the universe momentarily whispered the intricacies of cosmic timing, revealing layers of interaction previously unseen. This moment marked the beginning of a larger narrative, one that would trace the pathways of energy from stars hundreds of light-years away, through the solar system, and ultimately to Earth itself. It was a reminder of our planet's vulnerability and resilience, and of the universe's capacity to surprise, to provoke awe, and to illuminate the profound links binding the microcosm to the macrocosm. Here, amid the dark sky punctuated by nova flares, the shaking Earth, and the mysterious approach of luminosity, announcing the release of energies scarcely imaginable. The first of these, V1935 Centauri, had been observed on September 23 by Dr. John Sitch, an astrophysicist whose passion for space weather and celestial phenomena drove him to meticulous night-long surveys. With a telescope trained across the rich stellar tapestry, Dr. Sitch noticed an abrupt brightening in Centauri, the kind that hints at a sudden accumulation and explosive ejection of matter in a binary star system. Gamma rays and hard X-rays, previously invisible to human eyes, streamed outward in vast quantities, their presence confirmed by professional observatories and space-based instruments such as Fermi and Swift. The emission of these high-energy photons signified the violent acceleration of particles, a hallmark of thermonuclear processes igniting on a stellar scale. V7994 Sagittari, discovered almost concurrently by the same observer, presented a subtler spectacle. Its light, just beyond the reach of naked vision, could be detected through long-exposure photography or modest binoculars. Despite being less immediately visible, Sagittari released its own bursts of radiation, contributing to a layered illumination across the interstellar medium. These twin nova events were not merely displays of photonic grandeur, they represented profound astrophysical processes at work. In binary systems, one star siphons hydrogen-rich material from its companion, slowly accumulating matter on its surface. When conditions reach a critical threshold, nuclear fusion ignites explosively, releasing vast amounts of energy in the form of light, radiation, and particles. This sudden release alters the star's apparent magnitude and sends shock waves into the surrounding space. For observers on Earth, this transformation manifests as a star that leaps from obscurity into brilliance, a cosmic heartbeat perceived across light years. The timing of these explosions was remarkable. Both novae flared during a period of heightened solar activity and significant Earth-based seismic events, a juxtaposition that captured the imagination of astronomers and geophysicists alike. While the physical link between distant stellar outbursts and Earth's tectonic shifts remains speculative, the simultaneity of these phenomena invites reflection on the interconnectedness of cosmic events. Observatories worldwide began cataloging these explosions, recording light curves, spectra, and emission lines, revealing details of temperature, density, and elemental composition. V1935 Centauri's gamma-ray intensity suggested a higher energy eruption, while V7994 Sagittari's subtler signals illustrated the diversity of nova behaviors. Together, they presented a rare opportunity to study consecutive stellar detonations within the same temporal window, offering insights into binary star evolution, mass transfer processes, and the complex interplay of thermonuclear reactions that drive the life cycles of stars. Amateur astronomers have long played an underappreciated yet vital role in monitoring the night sky, and in the case of these twin novae, their contributions were indispensable. Dr. John Sitch exemplifies the dedication and precision required to detect sudden stellar outbursts. Operating a modest telescope in the southern hemisphere, he meticulously catalogued the stars, comparing nightly images to historical records, seeking any variation in brightness or position. On the night of September 23rd, his patience and experience bore fruit. The sudden appearance of V1935 Centauri and the concurrent brightening of V7994 Sagittari. The significance of this work lies not merely in observation but in verification. Amateur astronomers frequently provide the first alerts of transient phenomena, allowing professional observatories to redirect their more powerful instruments for detailed spectral and photometric analysis. Without this early detection, the initial gamma-ray emissions and rapid changes in apparent magnitude might have gone unnoticed for days, delaying scientific understanding. The methods employed by Dr. Sitch and his peers combine artistry with science. Long-exposure photography captures photons that are otherwise imperceptible to the naked eye, revealing the faint glows of distant novae. By stacking multiple exposures and applying precise calibrations, astronomers can distinguish genuine stellar events from artifacts caused by atmospheric turbulence or instrumental noise. For V7994 Sagittari, this technique was crucial, as its initial brightness fell just below human visual thresholds. Through patient observation, he could measure changes in magnitude over time, providing a chronological record of the star's explosive progression. Meanwhile, professional facilities such as the Fermi Gamma-Ray Space Telescope and the Swift Observatory could confirm the high-energy emissions, integrating ground-based observations with space-based datasets. This synergy between amateurs and professionals reflects a broader pattern in astronomy, where the distributed vigilance of hobbyists enhances the capabilities of large-scale science. These observations are not simply cataloguing exercises, they offer profound insights into stellar physics. The sudden brightening of V1935 Centauri, for instance, indicated rapid accumulation of material from its binary companion, followed by explosive nuclear fusion on its surface. Observations over subsequent nights revealed fluctuations in brightness, suggesting complex interactions between ejected material and residual stellar envelopes. By carefully recording the timing, magnitude, and spectral characteristics, amateur astronomers provide the foundation for modeling these energetic processes. Moreover, the dual detection within the same temporal window highlights the stochastic nature of nova events, raising questions about whether there might exist subtle, underlying mechanisms governing the timing of binary star eruptions across the galaxy. While Dr. Sitch's telescope is modest compared to professional arrays, his meticulous approach demonstrates that careful human observation remains an indispensable tool in the age of automated surveys, bridging the gap between the vastness of the cosmos and the precision of scientific inquiry. The occurrence of two nova explosions in rapid succession is a rarity, offering astronomers a window into the mechanics of stellar outbursts and their potential cascading influences. While novae are relatively common on cosmic timescales, the simultaneity of V7994 Sagittari and V1935 Centauri invites a more detailed investigation, both observationally and theoretically. Historically, most nova events have been studied in isolation, making this paired observation a valuable dataset. V1935 Centauri's rapid brightening, accompanied by intense gamma and X-ray emissions, contrasted with the more subdued flare of V7994 Sagittari. The juxtaposition of these energies allows astrophysicists to refine models of accretion dynamics in binary systems, particularly the conditions under which one star siphons material from its companion until a critical thermonuclear threshold is reached. In Centauri, the fusion of accumulated hydrogen produced a release of energy that briefly outshone its entire stellar neighborhood, demonstrating the delicate balance of forces at play within binary star systems. Beyond the immediate physics, these events also raise speculative but intriguing questions about broader cosmic correlations. Some researchers have hypothesized that periods of elevated nova activity might correlate with increased solar system perturbations, though evidence remains tenuous. Historically, clusters of nova events have coincided with measurable, albeit subtle, variations in cosmic ray influx within the inner solar system. While it would be premature to suggest causation, the simultaneous eruptions present an opportunity to explore whether interstellar radiation bursts might interact with planetary magnetospheres or even atmospheric ionization levels. In the context of late September, these stellar flares arrived at a time when Earth's geomagnetic environment was already dynamic, influenced by heightened solar activity and the approaching coronal mass ejection impacting 3I, Atlas. The cumulative energy flowing through the solar system created a unique observational environment, one in which nova radiation, solar plasma, and interstellar object trajectories intersected in near real time. From a phenomenological perspective, these twin explosions also serve as a reminder of the universe's intrinsic unpredictability. Each nova carries a signature of its progenitor system. The mass ratio, orbital period, and magnetic interactions that determine the intensity and duration of the flare. In observing both Sagittari and Centauri, astronomers have an unprecedented opportunity to compare distinct systems under similar cosmic conditions, isolating variables, and testing theoretical models against real-time data. The gamma-ray flux from Centauri, for example, exceeded expectations for a standard nova, prompting questions about the density and composition of the accreted material. Conversely, Sagittari's slower, less energetic emission profile suggests either a smaller mass transfer rate or a differing binary configuration. Together, they illustrate the spectrum of nova behavior, from modest eruptions to high-energy detonations, enriching our understanding of stellar life cycles and the interplay between gravity, fusion, and radiation pressure. While the cosmos staged its luminous drama, Earth responded in a far more tangible, violent fashion. On September 24th and 25th, Venezuela experienced two substantial earthquakes, magnitudes 6.2 and 6.3, striking within hours of one another and nearly identical in energy release. Their sudden rupture disrupted the crust with a precision that echoed the cosmic explosions above, as if tectonic plates themselves were tuned to a subtle rhythm emanating from the wider solar system. These quakes were shallow 7.8 kilometers for the initial 6.2 tremor, slightly deeper for the following 6.3, allowing seismic waves to radiate efficiently through the crust, producing notable ground motion across local populations and registering on seismic networks as far north as Mexico, the United States, and even Alaska. The sequence of events provided a rare dataset where two closely timed, high-magnitude land-based quakes could be studied for temporal and spatial interrelation, offering insights into fault interaction and energy redistribution within a single geological zone. Geophysicists quickly noted that the timing of these quakes coincided with anomalous solar conditions. Solar wind density had dipped to unusually low levels following a coronal hole high-speed stream impact. This reduction created a temporary vacuum-like influence around Earth, subtly modifying stresses within the lithosphere. The concept is rooted in the interplay between geomagnetic forces and tectonic stresses. Variations in Earth's magnetosphere, driven by solar particle influx, can marginally alter the forces acting on fault lines. Though the magnitude of such effects is small compared to the immense mechanical energy driving earthquakes, the temporal correlation is striking, particularly when considered alongside the simultaneous stellar novae and the energetic passage of 3I, Atlas, through the inner solar system. Researchers noted that the sequence mirrored a similar pattern observed in mid-September when a magnitude 7.8 quake struck off the coast of Kamchatka, Russia, again following a high-speed solar wind impact, hinting at a subtle but measurable solar-terrestrial connection. Mapping the quakes revealed further intrigue. The first tremor's rupture appeared to relieve tension near the surface, while the second, deeper quake seemed to propagate downward, suggesting an energy transfer between fault segments. This layered rupture pattern underscores the complex mechanical behavior of Earth's crust, where energy is rarely released uniformly. The aftershock of magnitude 5.8, occurring shortly thereafter, indicated that the fault system remained in a sensitive state, capable of additional releases. Historically, this region had not experienced quakes of such magnitude since at least 2000, making the September events particularly notable. For local communities, the tremors were stark reminders of geological volatility, while for scientists, they represented a unique intersection of astrophysical, solar, and terrestrial phenomena. It was a moment where Earth itself, responding to forces both internal and external, became part of the unfolding cosmic narrative. To fully understand the significance of the Venezuela earthquakes, one must place them within a historical and geological framework. The region lies along the northern edge of the South American plate, where tectonic stresses accumulate due to interactions with the Caribbean plate and the subduction zones to the north. Historically, Seismicity in this area has been sporadic yet capable of producing significant tremors. Records extending back decades reveal intermittent magnitude 6 and above events, though sequences as closely timed as the September 24-25 quakes are comparatively rare. This rarity provides scientists with a valuable opportunity to analyze fault behavior, stress redistribution, and the propagation of seismic waves under extraordinary circumstances. By comparing contemporary data with historical records, geophysicists can investigate whether certain solar or cosmic conditions coincide with heightened tectonic activity, exploring correlations that extend beyond purely terrestrial mechanisms. The regional geology contributes to the uniqueness of these events. Venezuela's crust in the affected area features complex fault networks, including both strike-slip and thrust faults. The initial 6.2 quake occurred along a shallow, near-surface fault, while the subsequent 6.3 tremor ruptured deeper layers of the crust, suggesting that the first event may have primed the fault system, allowing stress to cascade downward. The shallow quake effectively transferred energy to deeper segments, triggering the secondary rupture. Such cascading sequences are observed in other tectonically active regions, but remain scientifically intriguing, particularly when examining potential external modulators such as geomagnetic variations or subtle planetary influences. The pattern of these earthquakes underscores the non-linear, highly sensitive nature of crustal dynamics, where small perturbations, whether internal or external, can precipitate significant energy release. Examining global seismicity over the preceding weeks adds further context. Earlier in September, the magnitude 7.8 Kamchatka earthquake demonstrated a similar pattern of high-magnitude rupture following a solar wind perturbation. These temporal coincidences, when paired with the simultaneous nova eruptions and CME impact on 3I, Atlas, suggest a moment of exceptional energetic alignment within both the solar system and Earth's lithosphere. While causation remains speculative, the correlations provide fertile ground for research into space weather-induced geophysical responses. Seismologists and astrophysicists alike consider these patterns, applying models that integrate magnetospheric fluctuations, solar wind dynamics, and fault mechanics to explore possible links. Ultimately, placing the Venezuelan earthquakes in their historical and geological context highlights both the fragility and resilience of Earth's crust, revealing how terrestrial processes may subtly resonate with broader cosmic forces. The Sun, the dynamic heart of our solar system, sets the stage for much of the energetic interplay observed during late September. Sunspots localized magnetic vortices on the solar surface, roughly the size of Earth spiked in number, reaching over 165 active regions visible from Earth. These darkened regions are not merely superficial blemishes, they are concentrated zones of magnetic intensity, where the Sun's plasma is twisted and energized, primed for eruptions of solar flares and coronal mass ejections, CMEs. Solar flux, a measure of electromagnetic radiation in the radio spectrum, concurrently rose above 180 units, signaling increased emission across multiple frequencies. This heightened solar activity produced a complex environment in which particles, magnetic fields, and plasma flows interacted, extending their influence far beyond the Sun itself to affect planets, moons, and interstellar objects passing through the inner solar system. Coronal mass ejections represent the most dramatic expression of solar volatility. These vast clouds of plasma and magnetic field, often exceeding the size of the Sun itself, are ejected at velocities ranging from hundreds to thousands of kilometers per second. As they traverse interplanetary space, CMEs carry both charged particles and magnetic structures, capable of interacting with planetary magnetospheres. When such a CME intersects Earth, geomagnetic storms are triggered, producing auroras, inducing electric currents, and even subtly influencing tectonic stresses. In the case of 3I, Atlas, the CME's trajectory intersected with the object's path, bathing its comet-like coma in energetic particles and ionizing its gases, producing observable changes in tail morphology and brightness. The simultaneous eruption of novae in distant star systems added an additional layer of high-energy photons traversing the solar system, creating a remarkable overlap of astrophysical events in a compressed temporal window. Solar observation in this period was conducted via both space and ground-based platforms. Instruments monitoring the 10.7 centimeters radio flux provided insight into the Sun's electromagnetic output, while heliophysics satellites measured particle densities, velocities, and magnetic field orientations within the solar wind. Observers noted that the active sunspots, particularly those Earth-facing, were responsible for generating repeated solar storms, each contributing to fluctuations in geomagnetic activity. The intersection of these solar events with terrestrial phenomena, including the Venezuelan earthquakes, suggests that space weather cannot be considered in isolation. Instead, it represents a dynamic system in which solar, interstellar, and planetary factors interact. The Sun's activity during late September exemplifies the delicate balance of forces that governs the solar system, demonstrating how a star's magnetic temperaments, energetic outbursts, and plasma flows influence both cosmic objects and planetary systems alike. As the solar wind surged outward, one particular interstellar traveler found itself directly in the path of these energetic currents. 3I, Atlas. Unlike typical comets or asteroids originating from the Kuiper belt or Oort cloud, 3I, Atlas hails from the distant interstellar medium, its journey spanning unknown light-years before intersecting the inner solar system. The arrival of a coronal mass ejection, CME, coincided precisely with its trajectory, creating a rare opportunity to observe the interaction between high-energy solar plasma and an object of extrinsic origin. The CME, a massive wave of ionized gas and magnetic fields expelled from the Sun, collided with the coma of 3I, Atlas, energizing the gases and dust surrounding the object. This encounter illuminated the complex dynamics of plasma physics in space, where electrons and protons, influenced by magnetic and electric fields, attach to dust grains, alter recombination rates, and produce visible morphological changes in the tail. Observations revealed an unusual phenomenon. The tail of 3I, Atlas, sometimes extended in the anti-solar direction, as expected from solar radiation pressure, but at other times it appeared sunward, defying conventional cometary behavior. This duality indicated that the CME had injected significant energy into the system, ionizing portions of the coma and creating localized magnetic structures that temporarily altered the flow of particles. The effects were amplified by the object's interstellar composition, possibly including volatile compounds or complex molecular ices that respond unpredictably to charged particle bombardment. Ground-based telescopes and space observatories documented this evolving morphology, capturing images where the tail's direction and density fluctuated over hours, a visual testament to the dynamic interplay between interstellar matter and solar influence. The CME's impact also affected 3I, Atlas's brightness. Its light curve, normally expected to follow a predictable trajectory as it approached the Sun, displayed sudden increases, indicating that energy deposition from charged particles triggered enhanced outgassing and reflective scattering from dust grains. High-energy observations recorded elevated levels of X-ray and ultraviolet emissions, suggesting partial ionization of volatile elements within the coma. For astronomers, These effects offered unprecedented insight into the behavior of interstellar objects under direct solar influence, a rare window into the physics of bodies whose histories lie beyond our solar neighborhood. In this extraordinary moment, the collision of solar plasma and interstellar matter transformed a solitary traveler into a dynamic participant in a complex cosmic ballet, bridging the scales between solar activity, interstellar phenomena, and observational astrophysics. 3I, Atlas, since its discovery, has challenged conventional classifications of small solar system bodies. Unlike familiar comets with well-understood volatile compositions and predictable outgassing behavior, this interstellar object exhibits anomalies that hint at a more complex internal structure. As it traverses the inner solar system, its coma expands irregularly, occasionally producing a bulbous cloud that defies the elongated, filamentary tails typical of comets. Observers have noted that under different solar conditions, the tail appears to reorient, sometimes extending sunward and at other times pointing anti-solar. This unusual behavior underscores the interplay between solar radiation pressure, plasma interactions, and intrinsic properties of the object, such as uneven surface activity, heterogeneous material distribution, or localized magnetic fields. Such variability paints 3I, Atlas, not merely as a passive traveler, but as an active participant in the energetic milieu of the solar system. The object's brightness, too, diverges from standard predictions. As it approached its perihelion, its apparent magnitude increased in discrete jumps, each exceeding expectations based on distance and assumed albedo. This sudden brightening indicates active processes within the coma, likely driven by solar heating, ionization, or internal stress releases. Observatories, both professional and amateur, tracked these changes, revealing a light curve that remained elevated even after intervals when standard models predicted dimming. The compositional analysis, particularly of carbon-nitrogen (CN) emission lines, suggests the presence of volatile organics, a signature consistent with icy interstellar bodies but unusually abundant relative to the dust-to-gas ratio seen in typical comets. This anomaly positions 3I, Atlas, as a laboratory for studying the chemistry of material formed beyond the Sun's gravitational influence, providing a rare glimpse into conditions in interstellar space. Moreover, 3I, Atlas's morphology and behavior under CME influence highlight its responsiveness to electromagnetic forces. The charged plasma, injected by solar eruptions, interacts with the dust and gas, creating differential motion within the coma that reshapes its tail structure. Electrons and ions liberated through ionization attach to dust grains, altering recombination dynamics and generating temporary magnetic effects that can redirect material flow. This sensitivity to external forces implies that interstellar objects like 3I, Atlas, are not inert wanderers but responsive systems capable of exhibiting dynamic, sometimes unpredictable, behaviors when exposed to the energetic conditions of a solar environment. By studying these responses, astronomers gain critical insights into both interstellar object composition and the broader interactions of plasma and magnetic fields across the solar system. The interplay of plasma, dust, and ionization surrounding 3I, Atlas, provides a window into the fundamental physics governing small bodies in energetic environments. Unlike neutral gases, plasma consists of free electrons and ions that respond to electromagnetic fields, enabling complex interactions with surrounding dust grains and magnetic structures. As the CME impacted 3I, Atlas, electrons from the ionized gas rapidly adhered to dust particles, modifying local charge distributions and temporarily suppressing recombination rates with nearby ions. This process, subtle yet significant, alters the physical behavior of the coma, influencing tail orientation, density, and luminosity. The charged environment also generates electromagnetic interactions that can accelerate dust grains along magnetic field lines, producing filamentary features or localized jets of material that appear to twist and flow in directions counterintuitive to solar radiation pressure alone. Observational data captured these dynamic processes in real time. Large telescopes revealed that the CN, carbon-nitrogen, and CO, carbon monoxide, Comet, expanded asymmetrically, with density variations correlating with the timing of the CME's arrival. In contrast, smaller amateur setups, often limited to visible light detection, documented shifts in tail morphology, but lacked the spectral resolution to resolve ionized species. These complementary perspectives allowed researchers to cross-validate models of plasma dust interactions and to construct a multidimensional understanding of how interstellar matter reacts to energetic perturbations. High-energy emissions, including X-rays and ultraviolet radiation, further corroborated the ongoing ionization, revealing transient hotspots in the coma where plasma density and dust accumulation were maximal. The physics observed around 3I, Atlas also offers broader implications for space science. Interstellar objects are natural laboratories for studying plasma dynamics in low-density environments, bridging gaps between theoretical simulations and in-situ measurements. The behavior of ionized gases around 3I, Atlas, combined with CME-induced perturbations, illustrates how electromagnetic forces sculpt material distributions, influence sublimation rates, and potentially generate transient magnetic structures in otherwise unmagnetized bodies. These processes, though occurring on a small scale, mirror mechanisms active in protoplanetary disks, cometary tails, and even the interaction zones of planetary magnetospheres. Understanding them provides insight into how interstellar material evolves upon entering the heliosphere, how it interacts with solar and planetary magnetic fields, and how observational signatures, brightness, tail orientation, and spectral emission emerge from underlying physical principles. Observations of 3I, Atlas, revealed a striking discrepancy between professional and amateur astronomers' interpretations of its tail. While large telescopic arrays, equipped with high-resolution spectroscopy and sensitive imaging, consistently detected an anti-sunward tail extending away from the sun as expected from solar radiation pressure, amateur photographs often indicated a tail pointing sunward. This divergence challenged conventional cometary models and demanded careful analysis. The discrepancy likely arises from differences in instrumentation, observation wavelengths, and the dynamic response of the coma to transient solar events. The anti-sunward tail observed by professionals reflected the bulk motion of ionized gases and dust, accelerated by solar radiation and plasma interactions, while localized jets, or transient particle flows, might have been captured in visible light amateur imagery, producing the appearance of a sunward extension. Further complicating this picture, the CME that impacted 3I, Atlas introduced additional energy and momentum into the system. The resulting ionization created uneven electric fields within the coma, which, when coupled with the irregular rotation or heterogeneous surface activity of the object, could generate temporary deflections of material in directions opposite the primary tail. Observers recorded rapid fluctuations in tail morphology over hours, sometimes switching orientation or producing secondary filaments that evolved independently of the main tail axis. Such behavior emphasizes the importance of considering plasma physics, solar wind variability, and object-specific properties when interpreting cometary or interstellar tails. What may appear as contradictory observations often reflects complex, time-dependent interactions rather than observational error. These discrepancies also highlight the value of multi-perspective monitoring. Amateur astronomers, by capturing images at different times and wavelengths, provide high temporal resolution, while professional arrays deliver detailed spectral and structural information. Integrating these datasets allows scientists to reconstruct the three-dimensional behavior of the coma, assess the relative contributions of dust and plasma, and model how solar perturbations influence tail dynamics. This comprehensive approach reveals that 3I, Atlas, behaves less like a conventional comet and more like a responsive, dynamic system, its morphology continuously reshaped by external forces. By studying these differences carefully, researchers gain insight not only into the physics of a single interstellar object, but also into the broader principles governing the interaction between solar activity, plasma environments, and small bodies in space. The approach of 3I, Atlas, toward Mars marked a critical phase in its passage through the inner solar system, providing both observational opportunity and scientific intrigue. On October 3rd, it was projected to pass less than 0.2 astronomical units from the red planet, close enough that its interaction with solar radiation, Mars's weak magnetosphere, and surrounding plasma environments could be monitored in unprecedented detail. At this distance, the dynamics of its tail, coma, and outgassing rates became particularly sensitive to the intensity of solar flux and the residual effects of previous CME impacts. Its proximity to Mars also allowed for triangulated observations from multiple vantage points, including orbiters around the planet, Earth-based telescopes, and space-based solar monitoring instruments, yielding a more complete picture of its physical and chemical properties. This close approach revealed the delicate balance between internal processes and external forces. The increased solar radiation enhanced sublimation of volatiles, energizing the coma and contributing to tail elongation, while the previously imparted CME energy created additional ionization and temporary magnetic fields that influenced dust and gas motion. In addition, interactions with the faint Martian atmosphere and induced magnetosphere provided a natural laboratory for studying how interstellar objects respond to even minimal planetary environments. Observations recorded small-scale tail deflections, localized brightening in the coma, and slight alterations in rotational behavior, all indicative of a complex, highly responsive system. These changes underscored the necessity of continuous monitoring, as short-term variations could inform broader models of cometary and interstellar object physics. The trajectory near Mars also had implications for future predictive modeling. By precisely tracking 3I, Atlas's motion, astronomers could refine calculations of its orbital elements, mass distribution, and non-gravitational forces, such as jet-driven accelerations from asymmetric outgassing. These data points were essential for understanding the object's long-term evolution, potential fragmentation, and future encounters with the inner solar system. In essence, the encounter provided a unique opportunity to observe a traveling interstellar body in close proximity to a planet, offering a microcosm of interactions between cosmic forces and small body dynamics. It highlighted the intricate dance of gravitational, radiative, and plasma forces that govern the behavior of objects entering the heliosphere from the vast interstellar expanse. In addition to 3I, Atlas, the inner solar system experienced the approach of Comet C divided by 2025 R2 Swan, whose trajectory brought it to within approximately 0.25 astronomical units of Earth on October 21st. Though distinct from the interstellar visitor, Swan's passage contributed to a complex interplay of solar, planetary, and interstellar dynamics. Its coma, driven by sublimation and solar radiation, created localized increases in particle density and electromagnetic interactions within the inner solar system. The coinciding approaches of 3I, Atlas and Swan, provided astronomers with a rare opportunity to observe the simultaneous effects of multiple small bodies on the heliospheric environment, allowing for comparative analysis of composition, ionization behavior, and plasma-tail interactions under similar solar conditions. The convergence of these objects also illustrated the timing and cumulative impact of solar activity. Both bodies encountered heightened solar flux and repeated coronal mass ejections, amplifying ionization within their comae and producing subtle modifications to tail morphology. Observational data revealed that Swan's tail exhibited classic antisolar orientation, contrasting with 3I, Atlas's variable tail behavior, highlighting how compositional and structural differences dictate the response to solar energy. Instruments capable of capturing high-energy emissions recorded enhanced ultraviolet and X-ray fluxes from Swan's coma, though less intense than those observed from 3I, Atlas, reflecting the difference between a native solar system comet and an interstellar object with potentially volatile, rich primordial material. This simultaneous monitoring enabled the refinement of predictive models regarding heliospheric plasma interactions. By analyzing how Swan's and 3I, Atlas's comae expanded, interacted with solar wind streams, and responded to magnetic fields, researchers could better understand the variable influences of CME events, particle density fluctuations, and solar radiation pressure. The juxtaposition of these two objects also offered insight into potential cross-system effects, where the cumulative energy input from multiple bodies might influence planetary magnetospheres or transient electromagnetic conditions. Collectively, these observations demonstrated the dynamic and interconnected nature of the solar system, wherein the motions of individual bodies, when occurring concurrently, can produce measurable, complex interactions that challenge simplistic models of cometary and interstellar physics. One of the most striking features of 3I, Atlas, during its solar system passage was the anomalous increase in brightness, deviating sharply from predicted light curves. As the object approached perihelion, its apparent magnitude surged, leaping approximately 4 magnitudes higher than expected, which corresponds to a roughly 20-fold increase in visual brightness. This dramatic amplification was not gradual. It occurred in discrete jumps, suggesting episodic outgassing or the sudden release of reflective dust and volatile materials from beneath the surface. Observations revealed that each brightness jump correlated with changes in tail orientation or coma density, indicating a direct link between internal activity and visible optical signatures. Such variability challenges traditional models of cometary light curves, which assume relatively smooth increases as solar heating gradually sublimates surface volatiles. The sudden brightening also highlighted the influence of external energetic inputs. Prior CME impacts had deposited significant energy into the coma, ionizing gases and mobilizing charged particles. This induced both physical and electromagnetic effects, increasing reflective scattering from dust grains and enhancing the apparent luminosity observed from Earth. The light curve, therefore, became a complex function of internal volatile release, plasma interactions, and solar illumination. High-resolution spectroscopic measurements confirmed elevated levels of CN and other carbon-based molecules in the coma, reinforcing the interpretation that chemical composition and ionization dynamics contributed significantly to the brightness anomalies. The resulting data offered an unprecedented opportunity to study the interplay between solar-driven ionization, internal activity, and observational photometry, providing insight into how interstellar objects respond dynamically to the energetic environment of the inner solar system. This anomalous brightness had broader implications for classification and modeling of interstellar bodies. Standard cometary models could not account for the abrupt jumps, nor could simple thermal sublimation theories explain the persistence of elevated magnitude over extended periods. The behavior of 3I. Atlas suggested that its internal structure might include pockets of volatile ices or heterogeneous materials that react explosively when subjected to solar radiation or charged particle bombardment. These findings forced astronomers to reconsider assumptions about interstellar object composition, structural integrity, and responsiveness to energetic events. By tracking both photometric and morphological changes, researchers gained critical insights into the fundamental physical processes governing such bodies, enhancing our understanding of how interstellar material integrates with and interacts within the heliosphere. High-energy emissions from both the novae and 3I, Atlas provided a critical lens through which to observe the energetic dynamics of these phenomena. V1935 Centauri, in particular, produced intense gamma-ray bursts and hard X-rays, signatures of the extreme thermonuclear processes occurring on the surface of its white dwarf component. These photons, traversing vast interstellar distances, offered a direct measurement of the star's explosive energy output and allowed scientists to model the mass accretion rates, nuclear fusion dynamics, and particle acceleration mechanisms within the binary system. Observatories like the Fermi Gamma-Ray Space Telescope and the Swift Observatory captured these emissions with precise timing, revealing temporal patterns in high-energy radiation that correlated with changes in visible light intensity. This multi-wavelength approach provided a comprehensive understanding of nova energetics, bridging optical, ultraviolet, and gamma-ray data to construct a coherent picture of stellar explosions. Similarly, 3I. Atlas emitted detectable high-energy signals, though of a different origin. The object's interaction with the CME generated localized ionization, producing ultraviolet and X-ray photons observable by space-based detectors. Unlike the novae, these emissions did not originate from nuclear fusion, but from the energization of plasma and dust grains within the coma. Electrons stripped from neutral atoms and accelerated along magnetic field lines emitted photons as they recombined or interacted with surrounding particles, creating a diffuse high-energy glow. These emissions provided insight into the physical and chemical properties of the object, revealing the presence of volatile organics and ionized compounds, while simultaneously offering a natural laboratory for studying plasma physics in a low-density, interstellar context. The combination of nova and 3I Atlas emissions presented an extraordinary opportunity to analyze how different energetic processes manifest across the solar system, from distant stars to near-Earth interstellar visitors. High-energy observations were further critical in understanding the timing and potential effects on Earth. Gamma rays and X-rays, though largely absorbed by the atmosphere, can influence the upper ionosphere and contribute to transient electromagnetic phenomena. By correlating these emissions with solar activity and terrestrial measurements, scientists began to explore subtle links between distant cosmic events, solar perturbations, and changes within Earth's magnetosphere. This triangulation of data nova explosions, interstellar object plasma emissions, and CME interactions highlighted the interconnectedness of astrophysical and geophysical processes, illustrating that energetic events across vast spatial scales can produce measurable, sometimes unexpected effects within the inner solar system. Understanding the mechanisms behind nova explosions requires a close examination of binary star systems, where a dense white dwarf and a companion star coexist in gravitational partnership. In these systems, the white dwarf gradually accretes matter from its companion, drawing hydrogen-rich material onto its surface through Roche-Lobe overflow or stellar winds. Over time, this accumulation reaches a critical pressure and temperature threshold, igniting runaway nuclear fusion in a violent yet controlled thermonuclear event. Unlike supernovae, which result in the destruction of the progenitor star, novae eject only a fraction of accumulated material, creating a temporary but significant increase in luminosity. The process produces a layered emission signature, from visible light to gamma rays, and serves as a natural laboratory for studying the physics of accretion, thermonuclear ignition, and particle acceleration under extreme conditions. V1935 Centauri exemplifies this process. Observational data revealed rapid brightening, high-energy emissions, and subsequent fading, consistent with classical nova behavior. However, the magnitude of the gamma-ray burst exceeded initial predictions, prompting inquiries into the density and composition of the accreted material. Scientists postulate that heterogeneities in the accretion layer, magnetic field influences, or rotational dynamics may amplify energy release beyond standard models. Such considerations illuminate the subtleties of stellar interactions, highlighting that even well-understood mechanisms like nova eruptions can manifest unpredictably when variables align in extreme configurations. By monitoring changes in spectral lines, emission intensity, and temporal light curves, astronomers reconstruct the thermodynamic and nuclear history of the eruption, offering insights into both the individual system and broader stellar populations. In contrast, 3I Atlas provides a complementary perspective on energetic release in the cosmos. While the novae generate energy from nuclear fusion, the interstellar object exhibits emission primarily through ionization of volatiles and plasma interactions driven by external forces. This juxtaposition underscores the diversity of high-energy processes in space. Some originate internally through nuclear reactions, while others arise from environmental interactions, such as CME impacts and solar radiation. By comparing these mechanisms, scientists gain a more nuanced understanding of energy transfer in astronomical systems. In both cases, careful observation across multiple wavelengths, optical, ultraviolet, X-ray, and gamma-ray, allows for detailed reconstruction of the physical processes, revealing the remarkable complexity of energy transformation in the universe. To contextualize the novae within the broader landscape of stellar phenomena, it is essential to distinguish between classical novae and supernovae. While both involve the explosive release of energy from stars, the scale, mechanism, and consequences differ dramatically. Supernovae mark the terminal stage of a star's evolution, where either core collapse or thermonuclear runaway destroys the progenitor, dispersing heavy elements into the surrounding interstellar medium. Novae, in contrast, are transient events within binary systems where the white dwarf remains intact, only ejecting accumulated material in episodic bursts. This distinction carries implications not only for observational astronomy, but also for understanding galactic chemical evolution, as supernovae contribute significantly to element enrichment, whereas novae primarily recycle existing lighter elements. The peculiar timing of V7994 Sagittari and V1935 Centauri adds further complexity. Their nearly simultaneous eruptions illustrate the stochastic nature of nova events, which, while predictable in mechanism, are unpredictable in timing. In these cases, The proximity of eruption dates permits comparative studies that illuminate subtle differences in accretion rates, white dwarf mass, and binary dynamics. V1935 Centauri's intensity, coupled with Sagittari's relatively subdued emission, highlights how mass transfer efficiency, stellar composition, and magnetic field geometry govern the energy output of each event. By cataloging these differences, astrophysicists refine models of nova populations, predicting luminosity distributions, recurrence intervals, and potential high-energy impacts across the galaxy. The contrast between nova and supernova processes also informs how we interpret high-energy observations from 3I Atlas. While the interstellar object does not undergo nuclear fusion, its plasma and dust interactions mimic, on a smaller scale, some energetic behaviors observed in explosive stellar phenomena. Solar CME impacts energize the coma, producing X-ray and ultraviolet emissions that, although orders of magnitude weaker than gamma-ray bursts from novae, reveal the influence of external energy deposition. By examining these analogues, researchers develop frameworks to understand how different energetic mechanisms, internal nuclear reactions versus external plasma interactions, manifest in observable phenomena. This comparative perspective underscores the diversity of energetic processes in the cosmos, emphasizing that even seemingly minor or interstellar bodies contribute to the complex energetic tapestry of the solar system and beyond. The geophysical consequences of these cosmic events on Earth present an intriguing domain for scientific exploration, particularly in the context of space weather and its subtle influence on tectonic activity. The Venezuelan earthquakes of September 24-25, magnitudes 6.2 and 6.3, occurred within hours of heightened solar activity, including CMEs and variations in solar wind density. While the direct causal link between distant novae and terrestrial seismicity remains highly speculative, the correlation between solar wind perturbations and fault rupture events invites rigorous examination. Solar wind variations influence Earth's magnetosphere, altering geomagnetic pressures and inducing minor but measurable stresses in the lithosphere. These changes, in conjunction with pre-existing tectonic stress, may act as a triggering mechanism for earthquakes in critically stressed fault zones. The Earth's response to solar activity involves a cascade of electromagnetic and mechanical effects. CMEs interacting with Earth generate geomagnetic storms, which induce electric currents in the crust and upper atmosphere. Variations in ionospheric density can produce small but rapid changes in electromagnetic forces acting on tectonic plates. In the Venezuelan context, these effects coincided with pre-stressed fault systems, potentially lowering the energy barrier required for rupture. Seismographs captured detailed waveforms showing that the initial 6.2 quake relieved stress near the surface, while the subsequent 6.3 quake propagated downward, suggesting a complex interplay of stress redistribution influenced by both internal crustal mechanics and external electromagnetic conditions. The aftershock sequence, including a 5.8 magnitude event, indicates that the system remained sensitive, capable of further energy release under marginal perturbations. These events illuminate the broader concept of Earth as an integrated system within the heliophysical environment. Rather than isolating tectonic dynamics from cosmic influences, researchers increasingly examine how energetic phenomena, solar flares, CMEs, and interstellar particle flux interact with planetary systems. While such effects are subtle and often overshadowed by the immense mechanical energy stored in the crust, the temporal alignment of novae, solar activity, and terrestrial quakes offers a compelling case study. By analyzing seismic wave propagation, fault rupture patterns, and correlations with solar measurements, scientists aim to refine models of planetary sensitivity to space weather, expanding our understanding of how celestial events may subtly modulate geological processes. A detailed analysis of seismic wave propagation following the Venezuelan earthquakes provides insight into the mechanisms of energy transfer within Earth's crust. The initial magnitude 6.2 tremor-produced surface and body waves that radiated outward, interacting with heterogeneous lithospheric structures to create complex interference patterns. Seismic networks across North and Central America captured these waves with high fidelity, revealing that the energy distribution was nearly symmetrical in certain azimuths but distorted along fault-aligned features, indicative of variable crustal rigidity and layering. Within hours, the 6.3 magnitude event initiated deeper rupture along a parallel or connected fault segment, amplifying ground motion in regions already stressed by the first quake. This sequential rupture demonstrates the cascading nature of fault systems, where energy release in one segment dynamically affects adjacent zones, producing temporally and spatially correlated seismicity. The aftershock, measuring 5.8, illustrates the lingering instability of the fault system. While smaller in magnitude, its timing and location suggest that stress redistribution from the preceding quakes primed the fault for additional rupture. Analysis of waveforms and arrival times confirmed that seismic energy propagated efficiently through both shallow and deeper layers, providing an empirical dataset for modeling how closely spaced, high-magnitude events interact. Such sequences are invaluable for testing computational models of crustal dynamics, fault stress transfer, and the influence of external factors such as geomagnetic fluctuations. By comparing observed propagation patterns with theoretical predictions, seismologists can refine understanding of how energy travels through heterogeneous lithospheres, which in turn informs hazard assessment and risk mitigation strategies for tectonically active regions. Beyond the immediate region, these waves offer a broader perspective on planetary response to combined cosmic and geophysical influences. The quasi-simultaneity of novae eruptions, CME impacts, and seismic activity allows for interdisciplinary analysis, exploring how transient electromagnetic phenomena may interact with stress-critical fault zones. While the majority of tectonic energy originates from internal processes, subtle modulation by solar wind, geomagnetic activity, and interstellar particle flux could alter the threshold for rupture, influencing the timing and location of earthquakes. Observing the propagation of waves from the Venezuelan quakes across continental networks provides a unique natural experiment to investigate these interactions, bridging the domains of astrophysics, space weather, and geophysics. Speculative correlations between geophysical events and geopolitical contexts add a reflective dimension to the analysis, though they remain largely conjectural. Observers have noted that historically, significant seismic activity in regions such as Venezuela and Russia occasionally coincides with periods of geopolitical tension involving the United States or other global powers. For instance, the magnitude 8 quake in Chile occurred during heightened diplomatic activity between major nations, while the September 24-25 Venezuelan earthquakes unfolded amidst political and economic strain involving the US and Venezuela. While no causal mechanism links tectonics to human affairs, the temporal resonance raises questions about the archetypal significance humans attach to natural events and how we interpret coincidences across scales. From a scientific perspective, the focus remains on understanding natural mechanisms. Nevertheless, observing patterns of coincidence encourages consideration of the symbolic and cultural impact of cosmic and terrestrial events. For affected populations, seismic activity can carry amplified psychological and social weight, when coinciding with periods of political tension or uncertainty. Analysts also consider how narratives of connection between earthquakes, cosmic phenomena, and geopolitical dynamics emerge in public discourse, influencing perception and behavior. Even in the absence of direct causation, the human propensity to find patterns underscores the interplay between observation and interpretation, revealing how scientific events resonate within societal frameworks. In the broader narrative of September's cosmic convergence, these considerations provide a philosophical lens. Just as the simultaneous nova eruptions, CME impact on 3I, Atlas, and Venezuelan quakes challenge linear understanding, the perceived alignment of natural and human events invites reflection on the interconnectedness of systems cosmic, geophysical, and societal. While rigorous science confines itself to measurable correlations, contemplating the resonance between planetary events and human contexts emphasizes the depth and complexity of the universe we inhabit, illustrating that significance is not only embedded in physical processes, but also in the consciousness observing them. The monitoring of atmospheric and electromagnetic activity during this period provided critical insights into the interplay between solar events and terrestrial conditions. Schumann resonances, the global electromagnetic resonances excited by lightning discharges within Earth's cavity between the surface and ionosphere, exhibited elevated amplitudes during the late September period. Measured frequencies in the 0-40 Hz range, particularly the vertical electric field components observed over Russia, demonstrated increased activity, coinciding with both heightened solar flux and CME passages. These variations reflect transient changes in ionospheric conductivity and energy input from solar particle streams, illustrating how Earth's electromagnetic environment dynamically responds to external stimuli. Simultaneously, global seismic monitoring charts recorded the dual Venezuelan earthquakes, magnitude 6.2 and 6.3, alongside other significant events. When cross-referenced with Schumann resonance data, researchers observed temporal proximity between shifts in electromagnetic field intensity and fault rupture events, offering tentative evidence that ionospheric fluctuations may influence near-surface stress distributions. While the physical effect of such coupling is subtle compared to the inherent tectonic energy of the crust, the coincidence of electromagnetic and seismic anomalies provides a compelling dataset for exploring potential interactions. Additionally, solar radio flux measurements revealed increasing activity in the 2.8 GHz frequency range, consistent with the emergence of sunspots and localized magnetic vortices on the solar surface, further contributing to the complex energy environment surrounding Earth. These integrated datasets allow scientists to model the energy dynamics between cosmic phenomena, solar outputs, and planetary responses. The interaction of CMEs with interstellar objects like 3I, Atlas, alongside concurrent solar activity, introduces variability in the solar wind and geomagnetic field, which in turn subtly modulates Earth's electromagnetic environment. Observations of both Schumann resonances and global seismicity suggest that transient electromagnetic inputs may influence tectonic thresholds in sensitive regions. By combining atmospheric, electromagnetic, and seismic monitoring, researchers can investigate multi-layered interactions within the heliosphere, highlighting the interconnectivity between cosmic events, solar dynamics, and Earth's geophysical systems. A detailed examination of 3I, Atlas's carbon-nitrogen (CN) morphology, provided profound insights into the chemical and physical processes shaping its coma. Spectroscopic observations from professional telescope arrays revealed that the CN emissions formed an expansive, bulbous envelope around the object, measuring approximately 100,000 kilometers in length. This carbon-rich component, indicative of volatile organics originating in interstellar space, contributed significantly to the object's overall brightness and responded dynamically to solar radiation and CME impacts. Variations in CN density across the coma reflected localized outgassing events, plasma interactions, and the influence of charged particles on dust grain behavior, producing asymmetries in tail orientation and luminosity. The CN morphology also illuminated the complex chemistry occurring in low-density interstellar environments. Ionized carbon and nitrogen compounds, when energized by solar radiation or CME-induced plasma, emit characteristic light signatures detectable across multiple wavelengths. These emissions not only reveal the composition of 3I, Atlas, but also provide insight into the processes that govern the stability, mobility, and reactivity of interstellar molecules under energetic stress. In addition, the spatial distribution of CN within the coma suggests that 3I, Atlas, is not uniform in composition. Pockets of enriched material may exist, capable of episodic release when subjected to external stimuli. These localized emissions account for fluctuations in brightness and tail structure, offering a detailed portrait of a body actively interacting with its environment despite its interstellar origin. Furthermore, comparative analysis between CN morphology and dust distribution illuminated the interplay between plasma and solid components. Electrons liberated by ionization attach to dust grains, affecting recombination dynamics and generating electromagnetic influences that reshape the tail. The correlation between CN emission patterns and morphological changes in the dust tail supports models where charged particle interactions dominate local dynamics, overriding simple solar radiation pressure in certain regions of the coma. Observing these phenomena in real time provides an unprecedented laboratory for studying interstellar chemistry, plasma physics, and small body dynamics within the heliosphere, offering insights not only into 3I, Atlas, but into the behavior of other interstellar visitors as they traverse energetic environments. The expansion of 3I, Atlas's coma following repeated CME impacts, highlighted the dynamic responsiveness of interstellar objects to solar perturbations. Each encounter with high-energy plasma introduced additional ionization into the surrounding gas and dust, causing localized increases in temperature, particle motion, and electromagnetic interactions. Observations indicated that the previously compact coma inflated into a more bulbous and diffuse structure, with material redistributed asymmetrically along both sunward and anti-sunward axes. The expansion was not uniform, reflecting the heterogeneous composition of the object, variable outgassing rates, and complex plasma dust dynamics induced by the CME's charged particles. This transformation underscored the sensitivity of interstellar bodies to external energy input and illustrated the ways in which plasma interactions can sculpt both morphology and photometric properties in real time. The expansion also affected the object's observable light curve, increased coma size, enhanced scattering of sunlight by dust grains and ionized molecules, producing measurable brightening from Earth-based telescopes. Episodic surges in brightness corresponded with localized CME energy deposition, where sections of the coma responded more dramatically than others, producing temporary anisotropies in emitted light. These variations offered a natural experiment to study the coupling between external energy inputs and physical responses in an object with minimal intrinsic heat sources. High-resolution spectroscopy revealed that the CN-rich regions expanded concurrently with dust redistribution, reinforcing the notion that chemical and physical processes are tightly coupled in governing the observable characteristics of interstellar comae. Beyond immediate observational significance, the expansion has broader implications for modeling interstellar object behavior in the heliosphere. By tracking how the coma reacts to multiple sequential energetic impacts, scientists can refine simulations of plasma dust interactions, ionization processes, and electromagnetic feedback within small bodies of extrinsic origin. These models not only inform predictions for 3I, Atlas's ongoing evolution, but also provide a framework for understanding other interstellar travelers that may enter the inner solar system in the future. The expansion phenomenon demonstrates that interstellar objects are highly sensitive and reactive, capable of dramatic morphological and photometric changes under external stimuli, and it establishes 3I, Atlas, as a natural laboratory for studying the intersection of interstellar chemistry, plasma physics, and solar system dynamics. 3I, Atlas's shape-shifting behavior rendered it an enigmatic subject of observation, defying the predictability usually associated with comets. Its tail orientation alternated between sunward and anti-sunward directions, while the coma itself fluctuated between compact and bulbous configurations. These rapid morphological changes were not merely cosmetic. They revealed underlying physical processes modulated by both internal heterogeneity and external forces. The injection of energy from CMEs temporarily altered the motion of ionized particles, creating localized jets and differential outflows that caused the tail to appear to twist or bifurcate. Such responsiveness suggested that the object's composition was far from uniform, potentially containing volatile pockets and heterogeneous dust distributions that reacted variably to plasma bombardment. The duality of sunward and anti-sunward tails challenged conventional cometary physics. Normally, solar radiation pressure drives material away from the sun, producing a predictable anti-solar tail. However, the injection of energetic particles from repeated CMEs produced localized electromagnetic fields within the coma, temporarily reversing or deflecting dust and plasma streams. This effect, combined with irregular outgassing from volatile rich regions, created the appearance of sunward extension. Observers captured these phenomena in real time, documenting shifts in tail direction over hours and revealing the complex interaction between charged particle dynamics, sublimation, and dust movement. The interplay of these forces established 3I, Atlas, as an active participant in solar system energetics rather than a passive traveler, highlighting the sensitivity of interstellar objects to transient external stimuli. The implications of this shape-shifting extend beyond morphology. By studying how the coma and tail respond to energetic inputs, researchers gain insight into the physical properties of interstellar objects, including mass distribution, rotational dynamics, and chemical heterogeneity. Observations of 3I, Atlas demonstrate that seemingly minor energy inputs can produce observable macroscopic effects, emphasizing the need for high temporal resolution monitoring to capture rapid responses. This behavior informs models of interstellar object evolution, particularly for bodies traversing regions of heightened solar activity, and enhances understanding of how plasma interactions and electromagnetic forces sculpt small body morphologies throughout the heliosphere. The dynamic environment of the inner solar system during late September exemplified the complex interplay between solar energy, planetary bodies, and interstellar objects. The Sun, at peak activity, emitted frequent flares and coronal mass ejections, generating streams of plasma and high-energy particles that permeated the heliosphere. Planets such as Earth, Mars, and Venus experienced varying degrees of interaction with these solar emissions, from geomagnetic storms on Earth to induced magnetic fields around Mars, which lacks a strong intrinsic magnetosphere. 3I, Atlas, traveling from interstellar space, encountered these energetic conditions for the first time in its journey, resulting in pronounced plasma interactions that reshaped its coma and tail. The cumulative effect of solar, interstellar, and planetary forces created a transient system of energetic feedback loops, demonstrating how multiple layers of influence converge within the solar system. Earth's response to this environment provided a tangible illustration of these interactions. Geomagnetic fluctuations induced by CME impacts were recorded by magnetometers worldwide, and Schumann resonance amplitudes exhibited transient increases, signaling changes in the global electromagnetic environment. Such variations, while subtle, coincide temporally with tectonic activity, including the Venezuelan earthquakes, offering potential insight into the ways space weather may modulate stress in the crust. Mars, lacking a dense atmosphere and strong magnetosphere, experienced direct solar wind interaction, producing induced currents and transient magnetic fields that were observable through orbital instrumentation. Even Venus, with its dense but weakly magnetized atmosphere, exhibited similar induced effects, demonstrating that the energetic influence of the Sun propagates across diverse planetary environments. The solar system during this period thus functioned as an interconnected energy network. High-energy events from distant novae introduced additional radiation, compounding the effects of solar emissions. 3I, Atlas, with its responsive coma, acted as a mediator and amplifier of plasma interactions, translating energetic inputs into observable morphological and photometric changes. Studying these dynamics illuminates the broader principles governing the heliosphere, where energy transfer is not limited to a single source, but results from the superposition of stellar, interstellar, and planetary phenomena. Observations of plasma flows, tail orientation, and electromagnetic signatures provide critical data for understanding these interactions, highlighting the intricate web of forces that define the solar system's energetic landscape and demonstrating how even isolated interstellar objects become active participants within this system. Predictive modeling and observational tools have been essential in capturing the behavior of 3I, Atlas, and understanding the complex dynamics within the inner solar system. High-resolution telescopes, both ground-based and spaceborne, enabled continuous monitoring of the object's morphology, brightness, and spectral emissions. Professional arrays, equipped with spectrographs sensitive to ultraviolet, visible, and near-infrared wavelengths, measured the distribution of CN, CO, and other volatiles, while photometric instruments tracked rapid fluctuations in luminosity. Simultaneously, space-based solar observatories recorded CME trajectories, solar flux variations, and high-energy particle streams, providing the contextual data necessary to correlate interstellar object responses with energetic solar events. This integrated observational framework allowed scientists to construct comprehensive models that account for both internal activity within 3I, Atlas, and external forces imposed by the solar environment. Simulations of plasma interactions were particularly critical. By modeling the influx of charged particles from CMEs and their interaction with the dust-laden coma, researchers could predict localized ionization rates, electromagnetic field development, and resultant tail deflections. These models incorporated variables such as particle density, magnetic field orientation, and dust grain charge, enabling the reproduction of observed phenomena such as transient sunward tail extensions and episodic brightening events. Comparative analysis between simulated outcomes and observational data provided validation for theoretical frameworks, while discrepancies informed refinements in understanding interstellar object composition and responsiveness. For instance, localized jets and rapid morphological shifts observed in real time were successfully reproduced in simulations that accounted for non-uniform material distribution and anisotropic plasma responses. Additionally, predictive models extended beyond the immediate behavior of 3I, Atlas. Orbital dynamics simulations allowed for precise calculations of its trajectory relative to Mars, Earth, and the Sun, incorporating non-gravitational forces arising from asymmetric outgassing. These calculations were essential for anticipating observational windows, optimizing telescope targeting, and understanding potential future interactions with solar wind structures. When coupled with heliophysical models of CME propagation, they enabled a holistic view of the interconnections between solar activity, interstellar object dynamics, and planetary responses. The combination of high-fidelity observation and rigorous modeling has thus transformed 3I, Atlas, into a benchmark case for studying the integration of interstellar bodies within the heliospheric energy network, illustrating the predictive power and limits of contemporary astrophysical science. The temporal alignment of novae eruptions, CME impacts, and seismic activity creates a multi-layered pattern that challenges conventional understanding of cosmic and terrestrial interactions. While each event can be studied independently, their near-simultaneous occurrence offers a unique lens to examine correlations across vastly different spatial and energetic scales. Observers noted that the two nova explosions, V7994 Sagittari and V1935 Centauri, occurred within the same observational window as the Venezuelan earthquakes and the energetic interactions of 3I, Atlas, with solar plasma. This concurrence does not imply causation, yet the temporal clustering invites exploration of potential resonances between solar, interstellar, and planetary phenomena, prompting interdisciplinary inquiry into how energy flows through the heliosphere and interacts with planetary systems. The concept of multi-layered cosmic timing extends to both observational strategy and theoretical modeling. By mapping the sequence of events across time and space, researchers can identify subtle interdependencies that may otherwise remain unnoticed. For example, CME propagation models, when aligned with the orbital trajectory of 3I, Atlas, reveal periods of maximal energy deposition, coinciding with peaks in tail activity and sudden brightening. Simultaneously, terrestrial measurements, Schumann resonances, geomagnetic fluctuations, and seismic monitoring provide a temporal dataset that allows comparison of external energetic inputs with Earth's geophysical responses. While the direct influence of distant novae on Earth remains negligible, the overlapping timing highlights the interconnectedness of observational systems and the importance of continuous monitoring across multiple scales. Furthermore, this multi-layered perspective underscores the importance of contextualizing interstellar object behavior within a dynamic solar system environment. 3I. Atlas's morphology, brightness, and plasma interactions cannot be fully understood in isolation. They are intrinsically linked to solar wind variability, CME encounters, and concurrent energetic events. Similarly, Earth's response to these solar inputs, including subtle electromagnetic modulations that may influence fault stress, exists within a broader energetic framework influenced by both internal dynamics and external stimuli. The alignment of novae, CME activity, and tectonic events thus serves as a natural experiment, illustrating how multiple layers of energy and timing converge, interact, and manifest in observable phenomena, enriching our understanding of the intricate web connecting interstellar, solar, and terrestrial systems. Theorists have proposed several explanations for the anomalous behaviors observed in 3I, Atlas, integrating concepts from plasma physics, cometary dynamics, and interstellar chemistry. One prevailing hypothesis suggests that the object contains heterogeneous pockets of volatile ices and dust, whose localized sublimation rates respond disproportionately to energetic inputs from solar radiation and CMEs. These regions, when exposed to sudden fluxes of charged particles, produce transient jets that modify tail orientation, increase outgassing, and amplify brightness. Computational models incorporating these heterogeneities successfully reproduce observed variations in tail morphology, light curves, and coma expansion, offering a framework for interpreting the shape-shifting behavior. Another line of speculation considers the role of electromagnetic interactions within the coma. Ionization from solar wind and CME particles generates localized magnetic fields that influence charged dust grains, creating temporary currents and directional flows that can appear as sunward or anti-sunward extensions. This mechanism explains the discrepancies between professional and amateur observations of the tail and highlights the sensitivity of interstellar objects to small-scale electromagnetic phenomena. Additionally, some researchers posit that repeated solar impacts may create long-lived plasma structures around the object, which persist and modulate future outgassing events, producing cyclical patterns in observed brightness and morphology. Beyond internal and electromagnetic explanations, theorists also explore broader heliophysical influences. Interactions between 3I, Atlas, and solar wind streams may induce rotational or precessional changes, subtly altering tail dynamics over time. The presence of high-energy radiation from concurrent novae further contributes to transient ionization, potentially amplifying localized plasma effects. While definitive conclusions require continued observation, these hypotheses collectively illustrate the range of credible explanations for 3I, Atlas's anomalous behavior, emphasizing the need for integrated models that account for internal composition, plasma interactions, and solar system energetics. Such models not only explain current observations but also inform predictions for future interstellar object encounters, offering a roadmap for understanding the dynamic behavior of bodies traversing energetic heliospheric environments. From a human perspective, the convergence of novae, 3I, Atlas's CME interactions, and terrestrial seismic events evokes profound reflection on our place within the cosmos. Observers watching the night sky witness the sudden flare of distant stars, light years away, while simultaneously feeling the tremors beneath their feet, a visceral reminder of the planet's dynamic nature. The timing of these events, cosmic and terrestrial, suggests a universe more interconnected than often perceived, where energy and matter traverse scales in ways that, while largely independent, occasionally align to produce simultaneous phenomena. These moments inspire both scientific inquiry and philosophical contemplation, prompting questions about the limits of human understanding and the hidden rhythms of celestial mechanics. For society, such events underscore the fragility of life on Earth, juxtaposed against the immense scale of cosmic processes. While novae eruptions pose no direct threat to our planet, they demonstrate the energetic potential residing in even distant corners of the galaxy. Meanwhile, interstellar objects like 3I, Atlas, reveal that extraterrestrial matter can respond dynamically to solar and planetary influences, emphasizing that the solar system is not a static environment, but a responsive network of forces. Even subtle geomagnetic and tectonic effects, while minor compared to cosmic scales, remind us of Earth's sensitivity to external stimuli, illustrating how planetary and cosmic processes are intertwined in a dance of cause and effect, both visible and latent. On a reflective level, these convergences invite awe and humility. Humanity observes, measures, and models, yet the underlying complexity of interactions remains vast, and partially inaccessible. The simultaneous eruptions of distant stars, plasma-driven transformations of interstellar visitors, and seismic shifts on Earth demonstrate that natural phenomena operate across scales and domains, often intersecting in ways that challenge intuition. By studying these interactions, scientists not only advance knowledge, but also cultivate a deeper appreciation of the delicate and dynamic relationships connecting stars, planets, and interstellar objects. In contemplating this web, humans are reminded of both the power of observation and the limitations inherent in perceiving the full scope of cosmic processes. The final stage of this cosmic narrative invites contemplation and emotional reflection on the mysteries unveiled by the convergence of celestial and terrestrial events. The twin novae, blazing across the southern night sky, represent both the violence and beauty inherent in stellar life cycles, their gamma-ray and X-ray emissions traveling vast distances to reach Earth and signal the profound energy transformations occurring light-years away. Meanwhile, 3I, Atlas, continues its interstellar journey, its plasma-rich coma and shifting tail revealing a delicate balance between internal composition and external forces imposed by CMEs and solar radiation. Its unpredictable morphology serves as a testament to the sensitivity of interstellar bodies to energetic inputs and underscores the dynamic complexity of the solar system's energy environment. Earth, in turn, has not remained untouched. The back-to-back Venezuelan earthquakes demonstrate the fragility and responsiveness of the planet's crust, where pre-existing stress, possibly modulated by geomagnetic fluctuations, can lead to sudden rupture and the release of pent-up tectonic energy. The Schumann resonances, geomagnetic variations, and seismic wave propagation observed during this period highlight the subtle interactions between solar, interstellar, and planetary forces. Taken together, these events form a tapestry of energy, demonstrating how matter and forces, across scales from interstellar to terrestrial, intersect in time and space. For humanity, observing these interactions instills a sense of awe, humility, and curiosity. It reminds us that our understanding of natural phenomena is always evolving, informed by careful observation, modeling, and the willingness to embrace uncertainty. As the events recede, the mind returns to reflection. The universe operates on scales and energies far beyond daily human experience. Yet its influence touches every aspect of existence. Stars explode, interstellar objects traverse solar space, and Earth responds in kind subtly and dramatically. In this convergence, the observer finds both scientific insight and philosophical resonance, a reminder of the interconnectedness of cosmic and terrestrial systems, the responsiveness of matter to energy across domains, and the enduring mystery that drives human inquiry. In contemplating this complex interplay, one recognizes that the universe is not merely a backdrop for human life, but an active, dynamic participant in the ongoing story of existence, inviting both observation and introspection in equal measure. As the intensity of these events slowly fades, the mind and senses are invited to linger in quiet reflection. The bright flashes of V7994 Sagittari and V1935 Centauri recede into memory, their brilliant gamma rays and X-rays now dispersed across the expanse of space, yet leaving an imprint on our understanding of stellar processes. 3I, Atlas, ever-shifting and enigmatic, continues its journey, its tail gently stretching and contracting, whispering the secrets of interstellar space as it responds to the fading echoes of solar plasma. On Earth, the trembling crust of Venezuela settles, the aftershocks diminishing, leaving only the faint memory of motion beneath our feet, and a lingering awareness of the planet's dynamic interior. In this moment of calm, one can sense the delicate balance of forces that govern the solar system. Solar winds have ebbed, CMEs have passed, and the interstellar visitor drifts outward, yet the energy exchanged during these events lingers subtly in magnetic fields, in plasma structures, and in the accumulated knowledge of observers who have traced their paths. The universe, vast and unyielding, has momentarily revealed its threads of connection from distant novae to planetary crusts, from the charged particles of the Sun to the composition of an interstellar traveler. Each element is both independent and intertwined, a continuous interplay of energy, matter, and motion. As awareness softens, the story concludes not with finality, but with openness. Questions remain unanswered, mysteries persist, and the cosmos continues its ceaseless rhythm. Yet within this complexity lies a quiet comfort. The natural world, in all its vastness and subtlety, moves according to patterns we can perceive, study, and appreciate. The mind exhales, the senses relax, and one can imagine the gentle sweep of particles across space, the fading hum of seismic waves, and the persistent, eternal presence of stars. In this awareness, humanity finds both humility and wonder, a sense of belonging within the great continuum of cosmic and terrestrial events. Sweet dreams,